Okay guys, so these are your notes on periodic trends. Make sure you pause the video and write down everything that pops up on the screen. So the three main trends that we're going to talk about are atomic radius, ionization energy, and electronegativity. You already defined them in the packet, the little in the cards activity that we did, but you may not have fully understood what they were and also what the trends were within the periodic table. So atomic radius is the first one, and it's half the distance between the nuclei of identical bonded atoms. And the reason that we have to have such a complicated sounding definition is because it's very difficult to measure the radius of something that is a cloud. And so, an atom kind of has this fuzzy edge where the electrons are hanging out, and it's kind of hard to tell where it ends. So instead of saying, we're going to try to measure that distance, we just say, well, what if we had two hydrogens bonded together and we just measure half the distance between the two nuclei? Because the nucleus of each atom, is a very definite point in space, unlike the electron cloud. So that's what atomic radius is. And of course, you probably could already guess that hydrogen is a pretty small radius atom. But what is the general trend and why? Now, you should have probably already completed this in your packet, but you should have found that the radius increases down a group. And that should be pretty obvious because we're adding energy levels as we move down a group, like from hydrogen, which only has one layer or energy level. Lithium has 2, sodium has 3, potassium has 4. And the same thing would be true for any of our groups. As we go down a group, we're adding energy levels, so of course they're going to get much larger. The thing that may not have made a lot of sense to you is that as you move from left to right, the size actually decreases. So why is that? Okay, so if I zoom in on, let's just look at a couple of these guys up here in this in period 2 in the P block. Let's say I'm going to talk about boron and just compare boron to oxygen. Okay, so boron, let's say this is a boron nucleus. We'll make it green, a little boron nucleus, and it's going to be surrounded by a couple of energy levels. Boron's actually going to have 2 energy levels. And so is oxygen. Oxygen is going to be, there's its nucleus, not quite circular, but that's okay. And then first energy level and second energy level. And I've tried to draw oxygen a little bit smaller, and here's the reason. Oxygen has 8 protons. So if I look at the nucleus of oxygen, it has a +8 charge. And so these electrons that are in these energy levels, like let's say it's got 2 in the first energy level, in the case of oxygen it's got 6 in the second, those electrons are going to be pulled in towards the nucleus with more force than if we compare that to over here with boron. Well, boron's only got a +5 charge in the nucleus because its atomic number is 5. So it's going to have, 2 electrons in the first energy level. It only has 3 in the second energy level, but the important thing is this. Those 3 electrons are not being pulled in with a ton of force because that positive nucleus is only +5, whereas over here with oxygen is +8, and so those negative electrons which are attracted to the nucleus are going to be more attracted to +8 than they are +5. So oxygen is smaller. And then you could predict, of course, fluorine would be even smaller and neon would be even smaller than that. So those are our trends with atomic size. So the first one is the group trend. So we want to make sure that we have this in our notes. The group trend for atomic size is, or radius, is that radius increases down a group because the number of energy levels increases. Okay, that one is fairly obvious. The period trend is a little less obvious, and that's the one that we just talked about. Radius decreases from left to right because the nucleus is getting more positive. So we used, boron and oxygen as our example, where oxygen is more positive than boron, so it's going to pull those negative electrons in closer. Now the next trend, ionization energy, has a lot to do with what we just talked about. It is the energy needed to remove an electron. So let me draw another atom here. So let's say, so again, here's our little nucleus. This thing is going to have a certain number of energy levels. Okay, and of course electrons hanging out in those energy levels. So let's say it's got full first and second energy levels. 1, 2, 3, 4, 5, 6, 7. Throw one more in there, and let's just say it has only one electron in the third energy level. Now, first of all, this would be sodium, because sodium has just one electron in the third energy level. So I'm talking about sodium. And you saw sodium actually react, and you saw it react pretty well with water. And the reason for that is because it doesn't take a lot of energy to remove an electron from a sodium atom. And the reason for that is because it doesn't have a superpositive nucleus, and it's fairly large. If you remember, everything on the left-hand side, because atomic size is decreasing as we go to the right, that means everything to the left-hand side would be larger. And sodium then would be larger than magnesium, larger than aluminum, silicon, phosphorus, and on down the line, making it easier to remove that electron because that electron is negative and it's further from the positive nucleus. So ionization energy, we'll start with the period trend, because I just mentioned it, is that it increases from left to right because atomic size decreases and the nuclear charge, the charge of the nucleus, meaning the number of protons, goes up, so the nuclear charge increases. Okay, so that's our period trend with ionization energy. The group trend just has to do with size. So which do you think it's easier to remove an electron from? A big atom or a small atom? Okay, you should say a big atom, because for a big atom, there's a bigger distance from the nucleus, the positive nucleus, out to that electron that's being removed. So the group trend is that ionization energy, i.e., decreases down a group because radius increases. Again, making it easier to remove a negative electron the further it is from the positive nucleus. Okay, and the last trend we're going to talk about is electronegativity. Electronegativity is the pull that an atom exerts on shared electrons. So you probably talked about water molecules a little bit in biology. Water molecules are just a couple of hydrogens and an oxygen. They each have a positive nucleus, so oxygen there and a couple of hydrogens. And they're sharing electrons, and we'll talk about why later on. But they're sharing electrons in this overlap space, right here in green. So those negative electrons are attracted to these positive nuclei. But the question is, which nucleus are they more attracted to? Well, the answer to that question is, it depends on the electronegativity. So an electronegativity depends on two things. Bigger atoms generally are going to be less, the electronegativity is going to be less for bigger atoms because there's a bigger distance between the nucleus and the shared electrons. Also, though, the number of protons, the more protons you have in the nucleus, the stronger that pull is going to be. Therefore, if you have a pretty small atom that still has a pretty positive nucleus, like oxygen, right? So oxygen is a +8 nucleus, and it's still a pretty small atom because it only has 2 energy levels. Oxygen is going to have a really high electronegativity. So the period trend for electronegativity, En, electronegativity, increases as nuclear charge increases from left to right. So our greatest electronegativities are going to be found on the right-hand side. Things like oxygen and fluorine, if I go back up to my periodic table, things like oxygen and fluorine are going to have really high electronegativities. By the way, electronegativities don't exist for the noble gases because noble gases don't even share electrons. But fluorine would have our greatest electronegativity because it has a really positive nucleus, and it's also really small. So that brings us to our group trend, and that is that En decreases as size increases down a group. So then the last thing that I would kind of leave you with here is, first of all, let's make sure we have all our answers here. Electronegativity is increasing from left to right, and so is ionization energy. And then the opposite is happening here. Decrease, or decreases, on both counts. So atomic radius kind of has the opposite trend of the other two. So one way to remember this stuff is, if we're talking about atomic radius, the biggest atom on the periodic table is the one that is furthest down and to the left. The smallest is helium, which is furthest up and to the right. And then for like ionization energy, it's just the opposite. Helium has the biggest ionization energy because it's the smallest atom. Aside from hydrogen, helium is the one that is furthest up and to the right. And then electronegativity, same thing, only instead of helium having the biggest electronegativity, remember we're not including the noble gases because they don't share electrons, they don't have electronegativities, so therefore fluorine has the greatest electronegativity of all the elements.